Hello class and welcome to section 6.7 exponential growth and decay modeling data. In this first part here, we're going to discuss how to use the exponential growth and model decay formula in order to evaluate and more importantly now solve exponential equations. Let's begin by first going over some vocabulary and terminology here, that the mathematical model for an exponential growth or an exponential decay is represented by the same formula. It's represented by the formula of A of t, where our t is going to be our input value, or sometimes I write it like this, A sub t, again where t is going to be the input value. And the formula is very similar to the formula of continuous growth, the one that we talked about in continuous compounding interest. The only difference is that we're going to use different variables. Instead of p, we use the variable A sub 0, E, and instead of having the letter R for the rate, we use the letter K as the growth rate, and of course the input value of t. So this here is the formula we use for whether the situation is an exponential growth or exponential decay. Now, what's the difference between the two? Well, the difference has to be with the value of K, our constant growth or decay constant. K is going to represent that growth or decay constant. A of t or A sub t is the amount at some specific time t, and A of 0 is the amount at time 0, or in other words, the original amount. So if the value of k is a positive number, this number right here, this is going to result in this model representing the initial amount of a growing entity. And if that growing entity, A sub 0 being that growing entity, that amount is simply going to get bigger. It's going to grow at t is equal, from the moment of t is equal to 0. So look for a case in this example here and the graph that we see right here. So here we have some initial value, and this amount is growing higher because this value of k is going to be a positive number. So our entity is growing. Compare that to our entity, or an initial value decreasing and going downwards. Now recall that these exponential functions have a horizontal asymptote. So these things are never going to exceed 0. They're going to get as close as possible to 0 without actually ever equaling to 0, and never, for sure, never becoming a negative number as well. So when we're evaluating this, we should never end up with a number less than 0 or a negative number when we plug in a specific value for t. So if the value of k, like I mentioned, is negative, then we're going to have a decreasing entity, and like mentioned earlier, represented by this graph here on the right. So we'll turn to the next page. Let's talk about how, and let's review how to come up with these exponential models and how to simply evaluate them, because we've done that before. So let's suppose we have a population of bacteria that grows at a rate of 5% per hour. Notice that we're not saying that it's growing continuously, nothing like that. So we're going to just again assume that it is and use again the function, the formula provided on the previous page. So the initial population is going to be 200 bacteria. And we want to determine what the population is going to be in 10 hours. Well, first we need again the model that represents this situation. So using this formula, we're going to type in the corresponding values. A sub 0 is our initial amount, which we're starting off with 200 bacteria, and the only value that we also need is this value of k. Remember, E stands for the irrational number 2.71, and T, again, is going to be the number that we plugged in. First, I want to come up with the formula before I plug in that number T. Now, because we're doing at 5% per hour, our K, again, is increasing at 5% per hour, then that's going to represent a positive number here. So the formula for A sub T, or A of t, is 200 e to the positive 0.05 times t. And now that we have this formula, we can now use this formula, this model here, to come up with the population of this bacteria in 10 hours. So that simply means we want to evaluate A at t equals 10. So let's look at this example. So here I have decimals here on the left, and I'm going to do just simply evaluate this and replacing the value of t again with 10. Now recall again, in order to keep the 10 and multiply, that's 0.05 and 10 as the exponent, I need to put that multiplication in parentheses so it stays up there. If I don't do that and I put times 10, it moves it down there. So to multiply the 0.5 and the 10 as part of the exponent, I have to use parentheses to indicate that. So here's our answer. So we end up with a total of 329.7, which we'll estimate and round to the nearest whole number. You know what? I'm going to save this as A. So I'm going to round the letter A at 0 decimal places. So we end up with a 330. So now that we have that one, let's move on to the second example. So in the second example, suppose a pond has 35 frogs and the population grows at a rate of 11% per month. Now, how many frogs are there going to be in 2 years? So again, beginning with first being familiar and memorizing this. Again, you're going to need to know and have this formula memorized for your quizzes and exam, that this is your model for this situation. So our A of 0 is 35 frogs, and the K is 11%. So 11 out of 100, which is 0.11. So the model that represents this situation is A of t, or like this. That's going to equal to 35 e to the 0.11 t. And the question is asking us to evaluate this when the pond, how many frogs are going to be in this pond after 2 years, so in 2 years. Now, normally we would just simply use the number 2 here, but because the rate is increasing, the population of the frogs increasing as 11% per month. As I was saying, because it's increasing at 11% per month, we need to convert 2 years into months. The K, the unit of time for that K is being measured, always needs to match up with the unit of time that T is being measured. So it's a lot easier to convert this to months than it is trying to convert this into years. So since there's 12 months in 1 year, 2 years will have a total of 24 months. So for T, we're going to use 24. So we're trying to evaluate A when T is 24. And whether I write it like this or like this, it means the same thing. So putting in the number 25, and I'm going to do this off screen, but 35 times e to 0.11 times 25, just like I did the other example, that's going to end up equaling to a total of 490. And again, I just did the same thing in rounding my answer to the nearest whole number. Okay, now let's change gears here. Now, let's use this model now and apply to what we learned in the previous lesson on how to solve equations, exponential equations, now that we have this model. So solve the following exponential equation, modeling an exponential growth. So if the cattle population at a ranch is 12% per year, how many years will it take the ranch to have a total of 100 cattle if they initially, or they have right now, 25 cattle? So A of t equals A of 0 multiplied with E times KT. Let me get it thinner. So A of t equals A of 0 e to the kt. And the information that we're given is that right now, the initial number of cows is 25, and that the value of k is a positive 12% because it's growing over 100, so 0.12. So that means that the model here is 25e to the 0.12t. So what we're doing here is that we want to now figure out the time. So we want to figure out a time that the cattle is now going to be 100. So we don't know this value of t, but we do want it to be exactly 100. So we're going to end up solving an equation instead of evaluating this formula here and plugging in a number for t. So to do that, we're going to set this up. Since this equals to that, and we want this a of t, that same thing, to equal to 100, that means that these two things are going to equal to each other. So we end up creating an equation instead of evaluating something. So we're going to start by first solving this formula here, solving this equation by dividing the 25 from this side here. Now you can evaluate this and simplify that value, but I'm not going to do it, so you can see again, look what I'm getting my answer and where my answer is going to come from and how those correlate again to the numbers in this equation. So we have e to the 0.12t equals to 100 divided by 25, which obviously equals 4. And now to solve the equation from this point here, let me move this over, is that you're going to take the natural log to both sides. So I'm going to take the natural log to this side here. I'm going to take the natural log to that side there, which is going to cancel out the e. This will move this over here to the front by the power property of logs. And since this equals to 1, 0.12t times 1 is just going to simply be 0.12. In very layman's terms, you could think about this as just eliminating itself and the exponent becoming again the only thing left there. On the right side, we have the natural log of 100 over 25. And now we can divide both sides by 0.12. So t equals to the natural log of 100 divided by 25 divided by 0.12. And look at this answer right here and pay attention again to the format of this answer, because you're going to see that we're going to follow the exact same 3 steps every single time when solving these type of exponential equations. And the answer is going to look very similar to this every single time, of course, with the numbers changing, because the numbers are going to change in every different example. But notice where the 100 comes from. 100 is the amount we want to reach. The 25 comes from the initial value, and this 0.12 comes from that value of k. So let's just now plug this in and see what the decimal value for this, the decimal value or the number that this gives us. Okay, so here we go. So we want to type this into decimals. So I'll start by first inserting my division symbol. So I have my numerator and denominator. I'm going to type in ln of my ratio of 100 over 25. And then all of that, and pay very close attention to how I'm typing this in decimals, because I've seen people mess this up. So all of that gets divided by 0.12. So rounding this answer, I'm going to call it t for time. Let me save it as t. Rounding t to the nearest whole number is 12. So which is obviously 11.5 rounds up to 12 years. So it's going to take 12 years for the cattle, for this rancher to have 100 cattle if he starts off with 25, if the growth rate stays at this rate of 12% per year. So now let's consider this next example. So we have here a city's population is growing exponentially with a growth rate of 3% per year. The current population is 150,000. In how many years will the population reach 200,000? So first beginning again with coming up with a model to represent this, we're going to set up an equation. So we know that we're starting off with 150,000. The k value is 3 out of 100, positive, because again it's growing. So that's 0.03. And we are looking for a time where this population is going to be 200,000. Well, let me first write the model on top first. So the model that represents the scenario is A of t equals to 150k e to the 0.03 t. And the question is asking us to find a time where this amount is going to go up to 200,000, so another 50,000. So let's see. So just like before, we're going to set up an equation. I'm just going to write 150 because I'm going to divide out the thousands parts. So I'm just going to do that already. 0.03 t and set it equal to 200,000. And I'm ignoring the other three zeros because, as remember, the first step is going to be to divide the 150 out from both sides. So when I divide the 200,000 by the 150,000, those zeros are going to just reduce themselves out. So just for simplification purpose, I'm just going to automatically do that already. I won't simplify it any further because I want you to see something here. Okay? So you see, same first step as the previous example. From here, we're now going to take the natural log to both sides. That way, we can use the power property, pull this to the front, and since this equals to 1, this times that 1 is going to just be 0.03. We're going to divide by 0.03. And we get that t equals to the natural log of 200 over 150 divided by 0.03. And before we plug this into the calculator, again, I want you to pay very close attention to the format of t. Look how what t equals. Notice that we're still taking the natural log. This time we have 200. That comes again to the amount that we want to get to. The 150, the amount that we initially started. So that ratio, we're taking the natural log yet again of that ratio. And then that number is being divided by our k value right there. And the reason for that is because we're going to do the exact same 3 steps every single time. So our answer should always be in that format. And if you pick up on that pattern, you should be able to go seeing this immediately get to that eventually, because you'll be doing the exact same 3 steps. Now, I'm going to do the calculation off screen. I'm going to plug this into my calculator off screen. And by doing that, I will get that the value of t equals to 9.58. And when I evaluate or round it to the nearest whole number, that's going to be 10 years. So t equals. Okay, let's move on now to the third example. Here we're now going to look at exponential decay. And we're going to simply distinguish the difference between when we have a positive value for k and a negative value for k. And that again has to do just with the terminology. Like in this example here, suppose that a certain medication is eliminated from the body. So that means that this 3% is going to be a negative number. Now where the patient initially has 200 milligrams of this medication in their system. So how much of the medication is going to be left after 90 minutes? So A of t, again, the format and the setup is to replace and identify the initial value and the constant of decay, in this case here. So we're starting off with 200 milligrams, and our k value is a negative 3%. So negative 3 out of 100, so negative 0.03. And that's the only difference. That we're now simply using a negative number for this value of k. So our model would be A of t equals 200 e to the negative 0.003 times t. And the question is now asking us to determine how much of this medication is going to be left in their system after 90 minutes. Well, since our K is measured per hour, we have to convert our minutes into hours. And since there's 60 minutes in 1 hour, our 90 minutes will be divided by 60, meaning that the T, our time, let me move this over. Oh. Is going to be a total of 9/6, so 1.5. Which reduces, we could divide both by 3, so 3/2 as a decimal, like I said, is 1.5. So we're going to determine the amount when our time is 1.5 hours. So 200 e to the negative 0.03 multiplied by 1.5. So make sure again that when you're evaluating this, that the time is in the same unit as measure as what K is being measured in. Since the K again is a rate, so it's going to be measured in time as well. So then just plugging this in, just like we did on example 1A. I'm going to do this off screen, plugging this into my decimals calculator. I get that the value of 8.15 is approximately, sorry, let me see. Is 191.19 or 20. 199. I'll write 3 decimal values. So there's your answer. So moving along to the next example, very similar here. We suppose that a sample contains 80 grams of an iodine 131, a radioactive isotope, and the decay rate is 8.7% per day. How much is going to be left after 50 days? So given that the initial value is 80 grams, our constant of decay is negative 8.7%, which as a decimal is 0.087. We get that the model for this scenario is that A of t equals 80 times e to the negative 0.087 t. And since we're going to evaluate this at t is equal to 50, we're going to get the following. We're going to get 80 we're going to end up with a total of 104.28. So there is your answer. I'll do 3 decimal places also like last time. So let's now do 2 examples where we're going to now solve an equation with just a negative value of k. So an electronic device value depreciates, so that means it's going to decrease at 25%. If the initial cost is $1,200, how many years will the price value depreciate it to 400? So A of t equals a sub 0 e to the kt. We know that our initial value is $1,200. Our k is going to be negative 25%. So as a decimal, that's negative 0.25. And that makes the model this. And we're asked to figure out the amount at some unknown time to reach a dollar value of 400. So similar to example 2a and part A and part B, we're going to simply set an equation. So we're going to get our initial value multiply that with e and raise it to the negative 0.25t and set it equal to 400. Now I want you to pay, again, very close attention to the value of t and what t equals before we plug it into decimals. So the first step, again, is to divide out the initial value. So we're going to divide that number out from both sides. This is going to reduce, and e is raised to the negative 0.25t. And that equals to 400 over 1200. We're going to take the natural log to both sides. Same second step. This would reduce this and this out, giving us only negative 0.25t equals to the natural log, again, of this ratio. We'll now divide by negative 0.25, and that is literally the only difference, that we're dividing by a negative number here. And t equals to the natural log of 400 over 1200 divided by the negative value of 0.25. And because this is decreasing, notice that this ratio, the amount that we're dividing by this ratio, is going to be a number smaller than 1. So when I divide this and I look at the decimal value of this, I'll see that this is going to be some number less than 1, while on the growing one, the larger number was always on top. So, but again, the format, the order of this thing is the same. The 400 is the amount we want to get to. The 1200 is the amount we started off with. So we get that ratio, take the natural log of that ratio, and then divide it again by that k value there. And then plugging that into decimals, we get that the value of t is approximately 4.39. So when we estimate this to the nearest year, we're going to say it takes 4 years. So t equals. And just one last time for good measure, we have this last scenario here that a hot beverage cools according to Newton's law of cooling, where an exponential decay model function models the cooling rate. So suppose that the initial value, so let me write that down. So we're going to use again this model here. And suppose that the cooling rate is 7% per minute and the beverage initial temperature is 95 degrees. So A of 0 is 95 degrees. Our value of K, again, it's cooling. So that means that the temperature is going downward. So negative 7 out of 100. So negative 0.07. And that gives us the following model. So A of t equals to 95 e to the negative 0.07 t. And the question again is asking us to figure out a time where the temperature of this beverage is going to go down to 78 degrees. So A of t now needs to go down to 78. So we're going to set up our equation. Now here I'm going to skip all the steps and write in the answer before I show you the steps, and I know what the value of t is going to equal. The value of t is going to equal to the natural log of this 78 that I want to get to, divided by the 95 initial temperature of this beverage, and then divided by negative 0.07. Negative 0.07, yes. Okay, so let's see. Let's see if I'm right about this. So I'm going to go through again the procedure now through the steps. The first step is to divide both sides by 95. And we end up with e to the negative 0.07t equals to that ratio of 78 over 95. You see, that's there right there. Now to get rid of the e, we're going to take the natural log to both sides. Take the natural log to both sides. And negative 0.07t equals to the natural log of that 78 over 95. So you see that is that right there. And the only thing left to do now is to divide both sides of the equation by this value of k, so I can isolate the t. And that gives us that value there. This is going to reduce out, isolating the t, and there is what t equals, right there. So you see, same format every single time because you're doing the exact same 3 steps when solving these type of exponential equations. Now plugging this into the calculator, which I'll do off screen since I've shown you how to do it one time. Just look at that example, go back in that example and see how I typed it into Desmos. We're going to get that this equals to approximately 2.81, which can be estimated to 3. So it's going to take a total of 3 minutes for this thing to cool down to 78 degrees at a cooling rate of 7% per minute.